In Algebra 2, we first were introduced to solving rational equations. After we learned to add, subtract, multiply, and divide rational expressions, we were given the rational equation. Now, whenever you're working with fractions, it works best to have common denominators. So what we want to do is we want to determine what the least common denominator of these three fractions is. In order to do that, any of the denominators that can be factored, we're going to put in factored form. So I want you to notice that x squared minus, that should say 7x, plus 10 can be written in factored form as x minus 2 and x minus 5. So the least common denominator, they all have an x minus 2. If only these two had an x minus 5, we would have a common denominator. Well, we can make it have x minus 5. When you get a common denominator, though, you're literally multiplying the numerator and the denominator by x minus 5. The second fraction already has both of those, so I don't need to do anything to it. And then the third fraction, again, needs an x minus 5. When you get the common denominator, the denominators become something called negligible. That means they don't matter. I don't even need them anymore. So what I'm going to do is I'm going to create an equation with just the numerators. So 1 times x minus 5 is just x minus 5. Plus 1 is going to equal 6 times x minus 5. And I'm going to solve that equation for x. So the left-hand side simplifies to x minus 4. The right-hand side becomes 6x minus 30. I'm going to subtract x from both sides, and then I'm going to add 30, and I get 26 is equal to 5x. And then I'm going to divide by 5, and I'm going to get x is equal to 5.2. Now, as long as your solution to your rational equation does not make any of the original denominators equal to 0, then we're good to go. But every once in a while, we get a number that looks like it's a solution, but it's not. We called it an extraneous solution. So let's do a problem that will result in an extraneous solution so you can see what that does. So in this problem, remember, we're going to start by factoring any of the denominators that can be factored. This can be factored into t minus 4. So the least common denominator is going to be t minus 4. Now I'm going to start to skip some steps. The first fraction is missing a t minus 4. The second fraction is missing a t. The third fraction has both t and t minus 4 in its denominator, so I don't need to add anything to it. Remember I said in the last problem that the denominators become negligible? That's why I didn't write any of the denominators. I only worried about what I had to multiply each fraction by to get the common denominator. So now I have an equation that I know how to solve. I'm going to multiply these together. Notice that they're a product of a sum and difference. They're going to multiply to be t squared minus 16 plus 3t equals negative 16. Since it's a quadratic equation, we're going to set the equation equal to 0. So I'm going to add 16 to both sides, but hey, look, those end up canceling. You're left with t squared plus 3t equals 0. We're going to factor t out, and then we're going to perform the zero product property. So t equals 0 is one of the solutions, and t plus 3 equals 0, or t equals negative 3 is the other solution. The problem is, when you get your solutions at the end of the problem, you have to go back to the original problem, the one I wrote in black up here, and determine if either of those solutions makes any of the denominators 0. Because you can't have 0 in the denominator of a fraction. So we call solutions that make the original problem undefined extraneous solutions. Extraneous just really means like extra solution. You got an extra answer, but it doesn't make the original equation work. Remember we said our answers were t equals 0 and t equals -3. I want you to notice that if I plug in 0 for t, both of these fractions will have 0 in the denominator. So t equals 0 cannot be a solution. This must be the answer. Let me make this look better. It is t equals -3. There we go. Don't forget when you have problems that don't look like they have fractions, that they really do have fractions. So in this problem, a minus 5 over a equals 4. The common denominator is going to be 1a. So I'm going to multiply the first fraction by a, because that's what is missing in the denominator. The second fraction already has an a, and the third fraction is missing an a. So I get a squared minus 5 is equal to 4a. It's a quadratic, so we're going to set it equal to 0. A squared minus 4a minus 5 equals 0. Since it's a simple trinomial, I bet it can be factored. The two numbers that multiply to give you -5, but add to give you -4 are going to be -5 and +1. So using the zero product property, I'm going to find out that the solutions are 5 and -1. Will either of those answers make any of those three fractions undefined? The answer is no. The only answer that would have made it undefined is if we had gotten a equals 0. So since both of these solutions work, this particular problem has two answers. If you don't have more than two fractions in a problem, it's probably just a proportion. And instead of getting a common denominator, we're going to go about solving this problem by cross-multiplying, because it's just a proportion. So when I multiply, I get 9 times b minus 3 is equal to 3 times b plus 5. That's the easiest way to go about the problem. So 9b minus 27 is equal to 3b plus 15. I'm going to subtract 3b from both sides. And then I'm going to add 27. Let's see, and I get 42. So b is going to equal 7. So now I have to ask myself, does 7 make either of those denominators equal 0? And since it doesn't, that's good. That's the solution. What if I got one solution, and that one solution did make one or both of the fractions undefined? Then the solution would just be no solution. Remember, it's possible to have an equation that has no solution. Let's go back to the first problem we did. The reason I want to go back to this is because absolutely there is a graphing calculator technique for doing this. So what you can do on your graphing calculator is we're going to graph it, but I want to get this equation equal to 0. So I'm going to do this little trick to make this problem a lot easier to solve. In order to make this equation equal to 0, all I'm going to do is I'm going to subtract the 6 over x minus 2. And now it's equal to 0. So what I'm going to do is I'm going to graph this in y1 equals, and I'm going to graph this in y2 equals, and I'm going to determine where my graph hits the x-axis. That'll be my solution, just like we were doing with polynomials. Now, when you go plug this into your calculator, you have to be very careful. One of the things that I said was, if you're not sure if you should use parentheses or not, just use parentheses. So, for our purposes, and some of you may understand why you don't necessarily have to do this, but if you do it this way, you'll never have a problem. Put all your numerators and denominators in parentheses. The reason is because sometimes the numerators are not numbers, sometimes the numerators are expressions. those always need to go in parentheses. You don't even have to write it in factored form. Leave it in unfactored form. I'm running out of space, which is why I'm going to the next line here. So when you put this in y1 equals, it should look like this. And y2 equals should say 0. And then this is the graph that I get. Now, you're going to get a different graph. I'm working on an older version of a calculator. So you see this line that showed up on my graph? It's not going to show up on yours. So the blue squiggle, you don't see it. You see everything else. And I didn't realize this was going to happen. I have never seen a rational function have this weird little blurb there. And I thought that something was wrong with my calculator, and apparently it wasn't. So somewhere in here, the graph hits the x-axis. We want to find out where that location is. Using the 0 function is fine, but setting y2 equal to 0 and using the intersect function is much better. So go call up the intersect function and then move your cursor to the right until you see it pop up somewhere in that general area. When you do, hit enter 3 times, and it should tell you that the point of intersection of our graph with the x-axis happens at 5.2, which is the answer that we got doing it algebraically. But this was a lot less work. The other nice thing about the graphing calculator is that it will not give you extraneous solutions like algebra does. Extraneous solutions are a result of using algebra to solve rational equations. Now let's revisit t plus 4 over t plus 3 over t minus 4 is equal to negative 16 t squared minus 4t. If I want to utilize my graphing calculator to help me find the solution, I'm going to first set the equation equal to 0. And I'm going to do that by adding 16 over t squared minus 4t. Do you know why I added it? Remember, when you move terms from one side of the equation to the other, you change their sign. On the right-hand side, it was negative. So it's got to become positive on the left-hand side. All right, when you go put this in your calculator, you should put in, well, I guess we're not going to put in t's. We're really going to put in x plus 4 in parentheses divided by x plus 3 divided by x minus 4 plus 16 divided by x squared minus 4x, and make sure y2 equals 0. And this is the graph you should see, minus that line. You don't see that. So I see that somewhere in here, my graph is probably crossing the x-axis because I see the pixels start to go above the x-axis. So go to your intersect function and move the cursor till it's over here somewhere, and then hit enter 3 times. And it'll tell you that x equals negative 3, which is the solution that we found. Remember, when we did it algebraically, we got 2 solutions. We got 0 and negative 3. Because 0 isn't really a solution, it was extraneous. So with the graphing calculator, it doesn't find extraneous solutions. It only finds real solutions. And that is solving rational equations, both algebraically and utilizing the graphing calculator.